but I just wanted to finish what we had done. So I went back to the calculator page where we were, and I looked at what we had done right in here, right? What you had done here was plugging in 15 for length, taking the logarithm, multiplying by the slope coefficient, and adding the intercept coefficient, and you got this number. I went back to the notes page to explain that the log of the weight when the length is 15 was equal to that number. And then in order to get weight by itself, you would take the base, which is your 10, right? You would take this base and raise it to this power to give you your weight. And to that number, which by the way I got just by moving the up arrow and grabbing this to bring it down, and I get 48.6. I want to go back to my data and make sure that that 48.6 actually seems to fit. So I go back to my data, and I'm looking under length for something that's close to 15, and you can see that there's a 14.3 and a 16.8, and the estimate that I got, the 48, is somewhere between the 38 and the 69. So I'm feeling pretty happy about the number that I got. So I don't have an actual value when the length is 15, but I could use my model to come up with that estimate, and it looks like it would probably be pretty accurate. Okay, so the next step, there's another video that goes through the exponential model, but the next step I really want to know is, why does this work algebraically? So I added a notes page here, and I'm just going to walk through why does this work. So what we were doing was a power model, and the power model, if you remember, was y is equal to some constant multiplied by an x value, so your variable, to the power of p. Okay, so that's what my original model is. Okay, so what I'm going to do algebraically now is look at taking the logarithm of both sides. Sorry, having a little technical issue here. I want to undo that. So the log of the left side is log y would equal the log of the right side, and so since I took the log of both sides, the sides are still equal, so this is still working, right? And then I would like to use my properties of logarithms, which I'm guessing are a little bit rusty, to say that if I have things being multiplied inside here, then of the logarithm, this is the same as the log of each of them, but added together now. X to the p. Okay, then another property of log says that if I have an exponent, right, inside the logarithm, it's the same as bringing that exponent to the front and making it multiplication. So now what I have is log y is equal to log a plus p times log of x. So this is what I end up with if I simplify. Okay, so log of y, my variable y has had the logarithm taken of it, so if I'm graphing log of y on the y-axis, I'll get that. And log x also has the logarithm of the x variable, and that would be going on the x-axis. And what I'm having here is that log a is my constant. A is a number, right? So the log of a constant is a constant number. So I have a constant. This is your intercept coefficient of the line we found. Plus p is the power. This is also a constant, okay, times the log of x. So I have right here an equation that would be a linear equation if I graphed on one axis log of y and on the other axis log of x. So the last thing that you would do is, and I'm going to ask that you do this as an exercise before coming to class, start with the same idea, but instead of starting with a power function, start with an exponential function. And the difference here is that b is a number, right? So a and b are constants in this equation, and x is my variable as the exponent. But take the log of both sides just like we did here, and use properties of logs to break it up, and look at what's constant and what is your variable and what should be graphed together. Alright, so between this video and the other two, I think that you should be well set for Chapter 4.